So with that, let me begin the proceedings and let Patrick get started.
Great, thanks. Thanks, Michael and Jen, and welcome to everyone else. It's a real pleasure to be here. Recognized at least one face from last week in London. And so I'm going to indeed talk a little bit about limiting behavior in large networks. And in keeping with the theme, I will try to point out along the way much of what we don't know, as well as a little bit of what we do know in this context. So at a very high level, Mike just talked a little bit about the workshop goal, and I think it's a laudable one, unifying our theoretical and empirical understanding of, in particular, large-scale networks. I can say from personal experience that one of the things that makes this difficult for people from the theoretical side is that getting a hold of rich network data in the way that we would as statisticians ordinarily collaborate with people in other fields is rather difficult. And I think this is because some of the richest network data tends to be the same type of data that has the largest sort of security and privacy concerns. So reproducibility of published research is really important in this area. And I would say that it can be very difficult at times to really learn a lot about network data in depth if data sets remain proprietary. And I think we should all work to try to do what we can to help overcome that barrier. From the more mathematical point of view, so my interests and what I think the field needs is a coherent asymptotic framework for network analysis. And I think to have any kind of coherent mathematical theory, you need three main ingredients. For the theory to be relevant and inspired, you need mechanisms that generate data, right? So clearly we have that in spades. I think there's no question about that, and at least half of us here are intimately familiar with that. But we also need two other things. We need structure, mathematical structure, that facilitates analysis, right? So we need mathematical mechanisms and formalisms that help us understand how to put a variety of potentially disparate objects into a common framework and make sense out of them, right? And then the third thing we need are tools that flow from this mathematical structure. And it's important that the properties of these tools can be understood. We need to be able to have an understanding of everything from statistical sufficiency on one hand to algorithmic guarantees and runtimes on another. It's a very challenging area outside of the networks context. Bringing these two requirements together is something that Michael's talked about and written about recently. And in general, I think that there's quite a lot of progress to be made in this area. So anyway, so those are the three things I think we need. And as I said, right now, I would say we have one of them in spades. The other two are racing to catch up. So you can think of networks as big data, if you like. And if I remember right, the Simon's logo at the moment is sort of O of data or something like this. So it seems like a good opportunity to talk about this. What I've given you at the top here are three renderings of adjacency matrices of real networks. And maybe they're large, maybe they're not. It depends on how large you have to think n has to be truly large. But basically, these are just sort of pixelated images where I've listed the rows and columns of an adjacency matrix, and I've colored the corresponding diagram black if there's an edge between the ijth node and white otherwise. And that's in keeping with the notation that I've defined there. So typically when we want to make sense of these things from an asymptotic statistics framework, we start with the simplest possible non-trivial model. And usually to keep things easy, we assume that at some level there's some independence in the data. And so particularly, what we typically assume is that the links are somehow obtained as coin tosses in the simplest setting, right? And the model promulgated by Erdős and others is very, very simple. It has one single parameter, which is the biasness of a coin, and we just toss a coin n choose 2 times, and we get n choose 2 edges or non-edges, and everything's good. But of course, the challenge in statistics is to understand how do we couple the tosses in a sort of richer, more complex way. Right? If I have n choose 2 independent parameters and only n choose 2 observations, I can't really make inference in any sort of useful way. Right? On the other hand, one parameter surely isn't enough. So I thought I would start by talking a little bit about sort of the simplest possible framework for pushing past these basic models. Right? And what I want to think about, and what I'd like to ask you to think about, is the following question. How do we take a finite discrete combinatorial object, a graph, and turn it into or pass to an infinite dimensional analytical object instead? Okay? How do we go from a network to a function? And there's many ways that one could think about doing this, but it turns out there's at least one way that's particularly nice. And it'll be covered in detail by Peter later, so I won't talk very much about it, but it will get a mention a little bit later. And I'm interested in the case where we have three basic assumptions. So I'm going to say real networks typically exhibit these properties, and I think some of that at least is open to challenge. But as we look for a balance of mathematical tractability and practical utility, these three assumptions are workable. Okay? So the first one is that our networks of interest are often large. So we're interested in large sample limits. Okay? How large does n have to be? It depends on the complexity of your model. Depending on how you couple the edges in the network, your effective sample size could be as great as order n squared, or just barely larger than order n. Right? I'm going to assume that many networks of interest are sparse. I think there's good empirical evidence for this. And so what I'm going to say in this framework, in this asymptotic framework, is just that I'm going to make sure to allow my edge probabilities, or marginal probability of an edge, to be little o of 1. Okay? And then finally, in practice, at some level, we often need to model a lack of information. And one way to think about this is to imagine that we're interested in models for graphs that are essentially unlabeled. So if two graphs are isomorphic to one another, it means that they're the same, equivalent up to relabeling. And it's important to have asymptotic regimes that respect this type of invariance. Okay? So in other words, if you give me the data set and the order in which you list the nodes conveys no information, then I can think about what you've given me as kind of like an unlabeled graph. Right? Often in practice, as in the example I've shown here, we kind of play a game where we have covariate information about, for example, in here the political affiliations of the nodes in this network. We sort of hold out that information and we create a kind of clustering problem where we try to recover it. But at some level, just like we use IID-ness and ordinary statistical modeling, we have to kind of have a way to model a lack of information. Right? And thinking of the graphs as unlabeled is one way to do this. And I know it's something that Peter Bickel's going to talk about later on in the week. So if you take these three assumptions, you can begin to ask yourself, well, how do these inform our thinking? And as Michael alluded to, one thing you can take away from these three basic assumptions is that it is possible to write down a natural limit object for a graph that respects these three assumptions. And you get something akin to what we would call infill asymptotics. So think about time series. As the number of time series points that I observe goes to infinity, I can choose to do the analysis on the unit interval and imagine that my sort of sampling interval is something like 1 over n. Right? As n goes to infinity, I'm just, I'm dilating more and more finely into the unit interval. Right? And so the idea here is going to be very much the same. The notion will be that as the network size grows to infinity, I imagine these representations that I showed you before converging in some well-defined sense to a function defined on the unit square. Okay? So, I mean, it's almost like going from a digital image back to the analog world, if you want to think about it that way. And of course, life isn't that easy for many reasons. So largeness, we would then be covered. That's great. But sparsity causes problems because of things like effective sample size, how much information is really in the data as n grows, and also because of this issue of permutation and variance. I chose, of course, very, very special orderings for these three data sets. If we had more time, I could tell you about them, but it's a social network, a co-authorship network, and a student survey network. And in order to reveal this type of structure, I had to choose a very particular labeling for this graph. Otherwise, you wouldn't be able to see anything. Right? So if we begin at the simplest non-trivial model that I started telling you about before, we could imagine doing the following. So we jump up from a single parameter, which would give me an Erdos-Renyi type of graph, to n parameters, one per node. And if you're in social sciences and you want to think about this as a model-based version of degree centrality, you can do that. So you can think about each node having a propensity for connection. And in the standardization I've taken here, these are normalized. So every node gets a pi I. Pi I is between 0 and 1. And then I simply form connections independently by taking the product of pi I and pi j. So I have some propensity for connection. Michael has some propensity for connection. We shake hands, and with probability given by the product of our propensities, we link each other on Facebook or whatever. And so this is obviously a very, very simple model that yields some pros. For example, it's clear to see that if I take pi transpose, I get basically the mean matrix of the underlying adjacency structure. So I have a nice separable rank 1 model. And it also turns out that the network degrees, which I can get just by summing out across the rows of the adjacency structure, are sufficient to consistently estimate this vector pi. And there's a number of ways you can think about that. Many people have written about it. Peter's going to talk about it later this week. Basically, this is not the exact maximum likelihood estimator because it's, you think of this as a log linear model, and you'll see right away that the maximum likelihood estimator can't be written down in closed form. But nevertheless, you can show that to within a universal constant, depending on sparsity and some other things, you can basically, the degrees are essentially sufficient here. And there's other interesting behavior. You can get asymptotic normality in certain regimes. You can get phase transitions as the sparsity of the network shifts from dense to quasi-sparse to appreciably sparse to extremely sparse to ultra sparse, and we can make up more phrases all the way right down almost to the Poisson limit. Okay, the cons. So the cons are in some sense the same thing. When you have a model for which there exists a simple sufficient statistic, this tells you that that sufficient statistic captures all the structure that you can express with that model, right? So it's not often in life that we believe that a real data set would be well fitted by this type of model. That's why you often see it show up in graph clustering problems where it's a sort of natural null. Right? Nobody believes the null, but it turns out that you can think of doing sort of non-parametric anomaly detection, fitting a graph under this type of null, and then looking for patterns in the residuals, sort of the deviance residuals. And they'll often tell you something. To wit, modularity. Have a look at Mark Newman's modularity functional, and you'll see exactly the expected value of Pij under the null, appearing in the functional. So the other problem, of course, is that it's not really clear how to specify pi. That could be a weakness, that could be a strength. I'm going to say that from the point of view of practitioners, it's not really clear. Right? If I can't specify pi, how do I put down a good model? Right, a compelling or believable model, even if it's just a null model. So here's something you can do. You can increase the heterogeneity of this very, very simple sort of degree centrality model by doing the following thing, by adding a level of modeling hierarchy. So you can think of this as being Bayesian, if you like, if it suits you. Nothing will be harmed. Suppose we give pi a prior. Right? So I'll let each pi I be IID from some, let's say, density for now. G doesn't have to be a density, but that makes it easier the way that I've written it. And then I'll allow myself the opportunity to scale down the resulting probability of an edge by some value rho n. So this is purely for modeling convenience, let's say, to capture the fact that as n goes to infinity, if my pi's remain order 1, I'm going to get degrees that grow linearly with n in expectation, and that's not going to give me a structure that's very consistent with what we observe in real-world networks. Right? So rho n is just a scaling parameter, and that's why I've shown its dependence on n. And the nice thing about this model is, if I want to, I can just think about the inverse CDF method, and I can instead write down Pij directly as, again, rho n scaling, and now I take the inverse of the CDF of my density G, and I evaluate it at two independent uniforms, xi I and xi j. All right, so go across the whole network, let each node now have a latent uniform variable, xi, and I've just basically, by the inverse CDF method, rewritten this degree centrality model with an extra layer of hierarchy. So is that interesting? Is that helpful? It depends on your point of view. The good news is that we sort of added some potential for over-dispersion or heterogeneity. Perhaps the bad news, if you want to think about it, is that still somehow there is a kind of reproduction of G directly in the network degrees. So the way to think about this result is just the probability that any given degree di takes a value k ends up being asymptotically equivalent to this density G that we began with, evaluated at a scaled point, the sort of k over n times mu n, where mu n is just the overall expected edge probability. And that's basically telling you something that the probabilists have known for a long time, which is that as the network gets larger, the values of the degrees tend to concentrate around the sort of prior distribution that we started with. Okay? And one can make this, I mean, I didn't bother to write it, but one can make the statement much more precise with a multiplicative error bound and other kind of niceties. But the essential point is just that asymptotically, we sort of haven't added that much in a way, because we get right back to where we started. So again, this is really telling you, like, I started with something that was rank 1, and at the end of the day, when n gets large, like, as long as I'm not, and if I set rho n to 0, obviously this isn't going to work, right? But in any reasonable regime, this is basically going to be what's happening, all the way down to the Poisson limit. If I set mu n to 1 over n, or some constant over n, a theorem of this type will still hold. So all the way down to the limiting case where I have order 1 degrees as n goes to infinity.
Why do you have the indicator? Do you mean that the theorem is only true for k smaller than n times mu n?
No, there's something I wasn't going to talk about, but since in the spirit of open discussion, there's a cutoff effect. And the cutoff effect comes from sampling. I don't mean sampling like network subsampling. I mean like sampling distribution. So in other words, I have pi I, pi j. I generate an edge, but the product of two numbers less than 1 is always less than 1. And so when I instantiate this model, like, I'm not going to observe, with high probability, with exponentially large probability, or probability tending exponentially to 1, I'm not going to get very much far past what the mean of pi I and pi j are going to give me. So there's a kind of cutoff effect. If I would have written this differently, I would have actually written the survival function of a binomial here. And it basically looks like, it converges eventually in some sense in total variation to the indicator. And it basically looks something like this. So what you get is the product of two things. You get the density that you started with, which I don't know, maybe it looked like this. And then you get the product of these two functions together. And so what will happen in practice is that it'll look exactly like G, and then all of a sudden there'll be an exponential cutoff. And one can explain other models that have appeared in the literature that add parameters to explain this exponential cutoff in terms of what I've just written down for you. So when I say it's a consequence of sampling, I mean that basically Bernoulli variability does something to you, right? You can't just ignore that step in the process, or you won't get the right answer asymptotically. So there we go. So now, and in which Graphons finally arrive. So this has been lurking under the surface the whole time. What is this fundamental limit object that I've been talking about? Well, if you take the example I just gave you, which was rank 1, and we kind of convexify things and just think of taking a sum of k inverse CDFs, then clearly I can play the same game, right? And the reason I've bothered to make this a convex combination is just so that I keep the overall sort of balance of things here the same. And once you've done that, you have to ask yourself, well, like, why am I bothering? It's like, okay, like Mercer's theorem is begging me to do something here, right? Like, why am I bothering to just stop at a fixed finite expansion, right? And so in the theory of graph limits, which is something we'll hear more about today, Lovács and co-authors introduced the idea of something called a graphon. And a graphon is just a term for a function defined on the unit square that, okay, it has to be measurable, otherwise we can't really do much in probability terms. And we're going to let it be bounded, and that helps take care of some problems later. But basically, if the function is also positive and symmetric, then why don't I just write down a model for Pij that just scales this Graphon function f? Okay? You give any symmetric, bounded, measurable, positive function on the unit square, I will come up with a scaling regime such that the Pij's lie between 0 and 1 with probability 1, and we're off to the races. Okay? So why would you want to do this? Who cares? Is it a good idea? Et cetera, et cetera. So I will tell you a little bit of what I think of these things after first just pointing out that now we're going to get rid of the previous interpretation and renormalize things so that I recover rho n as the probability of an edge directly. And that's just a way of saying, if I want to dial in the asymptotic sparsity regime of interest, I can do it directly by controlling rho n. It doesn't really matter how I normalize f. I'm going to treat f as if it's a probability density and just go ahead and normalize it as I would a probability measure. So what does this let you do? Well, if you take a step back, ask yourself what we know about large graph limits. So one thing we know is Zemmoretti's regularity lemma. So the regularity lemma says, in essence, that eventually graphs that are sufficiently large start to behave like, in some sense, they can be subdivided into regular groups, blocks that behave similarly or quasi-randomly, if you want to think about it that way. And this regularity lemma has received a lot of attention in the purer communities, not just in combinatorics, but also in number theory and in analysis. And Zemmoretti, at his Abel Prize lecture, this was referenced from 2 years ago, it was now. So this has motivated people to think about dealing with networks that have large block-like structure. And one result in this direction that I'll just mention briefly to kind of set up what I'm going to tell you next is that if such a model is in force and the number of blocks or groups is controlled so it doesn't go too quickly, then as long as the graph is not all the way at the Poisson limit, one can consistently recover the groups. And so I've worked on this problem. Carl Roy's worked on this problem. It fits into the program on spectral graph theory that was mentioned at the beginning of the talk. And that's kind of basic flavor of result. But when we wrote this paper, we assumed that a block model was in force. This is called a block model. And that, for example, I knew the number of blocks and all these things. And that's fine. That's sort of traditional, standard frequentist asymptotic analysis where you assume a correctly specified model, you turn the handle, and you ask what maximum likelihood or profile likelihood will do for you. The more interesting thing is that I can also fit this model under model misspecification. So I can drop the assumption that the generative process is a block model, and I can go back to the Graphon assumption I gave you on the previous page. Right? I'm not going to worry about sparsity for now, because that's a complicating factor. But it turns out that even if you fit a block model to an arbitrary Graphon function f, then you get a kind of oracle inequality. The oracle inequality tells you that eventually the data, the noisy Bernoulli data, they sort of yield up information on f. And for this result to hold, f just needs to be measurable. Definitely doesn't need to be a block model. I don't need to know anything about it. I just know that it needs to be measurable. And before this result, the only result that was known had a logarithmic convergence rate, and that's basically down to Zemmoretti's lemma. Zemmoretti's lemma tells you something about the sort of uniform approximability of such things. So we improved this to a polynomial rate. We don't know right now which functions, if any functions, attain this rate. It certainly looks conservative in all the things that we come up with, but there's all kinds of things one could potentially do here. So, yeah, question?
What's the metric in which for this convergence?
Yeah, so I'll explain it in a couple of slides. it goes back to something I raised at the beginning, which is this issue of permutation and variance. So one has to define a metric that looks at sort of like the integrated mean square error of f, but allows for all possible rearrangements of the x and y axes. So
this is the cut metric?
yeah, so this is related to the cut metric. Exactly. Yes, thank you. Yeah, thanks. So there you go. So yes, this is essentially the cut metric. You can think of it as the cut metric. And for those of you who aren't familiar with the cut metric, it's exactly what I said. We sort of allow ourselves to rearrange the x and y axes arbitrarily, and we take the infimum overall rearrangements. Right? So how does this work? Well, the basic idea is you fit this block model idea that I described before. And a block model is basically just collecting or aggregating nodes into groups, looking at the corresponding sets of edges as blocks, and taking sample proportions over these blocks. Right? So I'm going to let z be the function that indicates which block a given node is in. So zi is in block A, for example. And I'm going to use h to count the size of each group of nodes. Right? And then I'll call capital H the sort of cumulative distribution function that arises if I think of ordering the blocks in a nice way, like the pictures I showed you, and then basically stepping through from one block to the next. So this H inverse of u could be used as a generative model, just as I used G inverse in the slides that I showed you earlier. Right? So we're just about done. I want to just give you one final result here, and then we can talk later about pros and cons. I'm going to define my non-parametric estimator of f by using the sample proportions over these blocks. And so all I do is I use this capital H function to just extend my block model so that it's defined on everywhere on 0, 1, cross 0, 1. And I estimate rho n hat by just counting how many edges are in the network and dividing by n choose 2. So the main result is that if you fit a block model by profile likelihood, and if things are not too nasty, then you can get a kind of universality of approximation. So what I do is I think of fitting a sequence of these models. I force the number of blocks to grow with n, and I control the average group size or the maximum and the minimum group size kind of to my advantage. And then as long as I'm not too sparse, so as long as, sorry, that's not actually polylog n, that's the degrees need to grow as polylog n. As long as I obey these conditions, then I can get convergence in the cut metric. And the main conditions that I need are that the effective sample size of every block has to grow rapidly enough that things behave asymptotically normally. Okay? So that's why I have to make sure that the expected number of edges in the smallest block is lower bounded by something that grows faster than log n. And on the other hand, I need to make sure that the kind of largest or average block size isn't so large that, that I'm not sort of zooming in gradually on this function that's defined on 0, 1 cross 0, 1. So I won't go into all the details of where these terms come from, but you basically, to get a result like this to work, it helps to have a kind of uniform continuity. So alpha tells you how smooth your function f is. It's the Holder constant, or the Holder exponent. And you pay a price according to that smoothness, or that lack of smoothness. You pay a standard profile likelihood price for not knowing the parameters in the model. And then you pay a third price to get the convergence of these underlying psi uniform random variables that I talked about a few slides ago. So I'll stop there. That's kind of where we are in this way of thinking, and I know we're going to hear some more about this morning, but let me bring it to a close there, and thank you very much. We can whatever you like. Thanks.
I guess unless there are short technical questions or clarifications, why don't we move on and then save it for the general discussion.
Good. Okay.
So I think next we